Okay, 10 past 10. Okay, beginning with exponential equations. And 24 interesting problems here, just to get started with. And these are exponential equations that don't require logarithms. So we begin with 4 to the 2x at 3 equals 1, and thus what power of 4 gives you 1, and the answer is 0, so 2x plus 3 equals 0. It's really strange how it always does that. 2x at 3 equals 0. So x is minus 3 over 2. And here we've got 5 to the something equals 5 to the something, so those things must be equal. And you add 2x to both sides and you get x equals 3. 3 to the something is 243. That's the fifth power of 3 right there. So 1 take 2x equals 5. So negative 2x equals 4. So x equals negative 2. Equivalent powers. So a must be 0. Here 3x take 2 must be 0. So x is 2/3. And here these are also equal. So 4p must be negative 1. So p must be negative 1 over 4. And just to check these 6. Okay. Agreement so far. It's all looking good. Okay. Agreement of powers. So a is 2. Likewise here. So x must be 2. Now here you add the exponents, surely. So 3m take m is equal to negative 2m. And that would be 2m equals negative 2m. And so m must be 0 itself. 2 to the x over 2 to the x, so that's 1. That must be 0. So x must be 0. Negative 3x plus x, just adding them, that'd be 10 to the negative 1. So negative 2x is negative 1. So x must be a half. Adding these together, they're equal. And just to check these 6. Okay, good. Looking good so far. Now, add these together. That's the third power of 4. Add these together. Negative 2x, take x, so negative 3x. And that's the third power of 6, so that must be the negative third power of 6. So x must simply be 1. That's the negative fifth power of 2. And that's just the fifth power of 2. So x must be 10. turn everything into power of 4, perhaps. So that there is 4 cubed. That's the square of 4, then raised to the negative 3x. So that's 4 to the negative 6x. That's the square of 4, then raised to the 3x take 2. So that's 4 to the 6x take 4. And so now we can say that 3 take 6x equals 6x take 4. Okay, so 3 equals 12x take 4. 7 is 12x. X is 7 over 12. Express everything in terms of powers of 3, because that's the fourth power of 3 right there. So on the numerator, we have 3 to the 12n plus 8. And on the denominator, we have 3 to the 5. Then that's raised to the negative n. So it's 3 to the negative 5n, just like that. These 12n add 8, then take away negative 5n. So in other words, add 5n. So 17n add 8 is equal to 4. So n itself must be negative 4 over 17. Now to check. Okay, agreement. Yeah, these are all in agreement. Okay, this is wonderful. Okay, so we express everything in powers of 3. That's the fourth power of 3 right there. Multiplied by, you just need to double the exponent up here. And that's, of course, that. Equals 3. So minus 4b is 3. So b is 3 over 4. The negative of 3 over 4. 3 to the negative 6x times 3 to the 2x equals 3 to the 3. Negative 6x add 2x is negative 4x. So if negative 4x is 3, then x is negative 3 over 4. Here, this is 6 to the negative 1. So that's all of that is raised to the, all of that is made into its negative self. That's 6 cubed. So that's turned into triple. That's 6 to the minus 3. So 6x minus 2 equals minus 3. So 6x is minus 1. So x is minus 1 over 6. These are all powers of 3. So that's the 3 to the 5. So 3 to the 5k add 10. Times 3 to the 4k take 2 equals 3 to the 2. Add them together now. 9k add 8 equals 2. Take off the 8 from both sides, so negative 6. 9k equals negative 6. So k equals negative 6 over 9. So k equals negative 2/3. Here, express everything in powers of 4. So that's 4 to the 2r times 4 to the 9 take 9r equals 4 to the 3. Add them together, so 9 take 7r equals 3. So 7r equals 6. And r is indeed 6 over 7, it appears. Here, express everything in powers of 2, so that's 2 to the 4. So quadruple that. 8p take 12. That's the second power. And equate them and combine them. 4p is 16, so p is 4. And check. Okay, all good. All good. Now to try this. Those were really enjoyable. Solving exponentials with logarithms. So in this case, you won't be able to do it without your calculator. So if 3 to the b equals 17, it's log base 3 of 17. And to the nearest 10th, well, we'll talk about this. Okay, so that's 2.57890192. That's what it says on the calculator, but you got to go to the nearest 10,000th. So there's to the nearest 10th, 100th, 1000th, 10,000th. So in places. So we say 2.5789. One 1.03222. One 1.5165. Okay, and to check. 579. Okay, this is an agreement so far. Okay. Log base 3 of 69, that's what A is. Log base 3 of 69, which is 3.8540 to the nearest 10,000th. 6 to the r is 51, so r equals log base 6 of 51. Log base 6 of 51, which is 2.1944 to the nearest 10,000th. 6 to the 9 equals 99, so n equals 6 to the n equals 99, so n equals log base 6 of 99. Which to the nearest 10,000th is 2.5646. 20 to the r equals 56, so r equals log base 20 of 56. Which is 1.3437 to the nearest 10,000th. And to check these next four. Yep. Okay, good. Agreement. Okay. In this case, divide then. So we have 18 to the 6x, 6 over 5. And then understand that 6x is log base 18 of 26 over 5. And then divide that by 6, and you'll obtain the right answer. Log base 18 of 26 over 5, all of that divided by 6. So it appears to be something very small, 0.0951. Now here, e to the x take 1 take 5 equals 5, so add 5 to both sides simply. Then do the natural logarithm of both sides. So if e to the whatever equals 10, then ln of 10 equals that whatever, right? But you should keep them on the same side. So that's 3.3026. That's what I believe anyway. Okay, here take 3. I mean, it's all 3, so it looks very tempting that you could do it, but 9 to the 9 to the n add 10 equals 78. So n equals log base 9 of 78. All of that take away 10. Add 5 to both sides, and then log base 11 of both sides. Oh, add 8 to both sides. Okay, so we've got 9.7005. I'll have to check these. Okay, so we're in total agreement. Okay, that's good. Now take 5 from both sides. So 16 to the n takes 7 equals 19. Then log base 16 of both sides. So n takes 7 equals log base 16 of 19. And then just add 7. So n is log base 16 of 19 plus 7. Which is about 8.0620. Take 6 from both sides, so 49. Like that. And then log base 20 of both sides. And divide both sides by negative 6, rather. Negative 6. That's what it should be. So log base 20, 49, divided by negative 6. negative 0.2165. There. Divide both sides here by 5, so we get 4 on the right. Log base 6 of both sides, so 3m equals log base 6 of 4. Then divide both sides by 3, so log base 6 of 4 divided by 3. And we get 0.2579. Add 5 to both sides, so we get 58 on the right. Log base 8 of both sides, so negative 5a equals log base 8 of 58. Then divide both sides by negative 5. And we get negative 0.3905. And check that those are right. The next 4, I mean. Okay, total agreement. Right, next. Okay, that's a decimal. Add 9 to both sides, so 5 on the right, divided by 3.4. So e to the 2 take 2n equals 5 over 3.4. Then natural log both sides, in other words, ln. So 2 take 2n equals ln of 5 over 3.4. Take 2 from both sides and then divide both sides by negative 2. So n is equal to that, take away 2, divided by negative 2. Just type that in and you'll be fine. All of that, take away 2. And all of that divided by negative 2. And we get 0.8072. Here, add 3 to both sides, so we get negative 20 on the right, divided by negative 6, so we get 10 over 3. So 8n at 8 is ln 10 over 3. So n is ln 10 over 3. Take 8, all of that divided by 8. Which is negative 0.8495. And this one, add 1 to both sides, so negative 2 on the right. Negate both sides, so e to the negative of that equals 2. Okay, ln both sides. Add 1 and then divide by negative 3.9. Here add 10 to both sides, so negative 7 divided by 2, 7 over 2, and negate both sides as well. 7 over 2, so 7v add 5 is ln 7 over 2. Wait. Okay, that's fine. So V is ln 7 over 2, take 5, all divided by 7. There. Oh, yes. Make sure these are right. Okay, 17, 18, 19, 20. Okay, that's all in agreement there. Okay. Okay, next 4. Add 6 to both sides. Divide both sides by negative. No, take 6 from both sides, beg your pardon. Divide both sides by negative 3. And so we then have e to the 7a at 9 equals 4. Ln of both sides. Ln of 4. So 7a equals ln of 4 take 9. So a equals ln of 4 take 9 all over 7. Ln of 4 take 9 all over 7, which is negative 1.0877. Take 6 from both sides, so we have negative 64 on the right. Divide by negative 3. 64 over 3. E to the 9x take 1 equals 64 over 3. So 9x take 1 equals ln of 64 over 3. Add 1 to both sides and divide by 9. Okay, so ln of 64 divided by 3 plus 1. Divide that by 9. 4511 there. Take 5 from both sides, so negative 53.4. Then negate both sides. So e to the 6 take 9p equals 53.4. So 6 take 9p is that. Take 6 from both sides and divide both sides by negative 9. There. Okay, add 6 to both sides. So negative 60 divided by negative 10. So e to the 2 take 2b equals 6. Ln both sides. So 2 take 2b equals ln of 6. And then ln of 6 take 2b. B is ln of 6 take 2, all divided by negative 2. Zero 0.1040, 0.1041. Okay, checking the next 4 now. Seems all good. And next up, this one here. So add 4 to both sides, divide by 6. Learn on both sides. Then add 10 and divide by -4. So we get -3.1032. And the last one. Add 4 to both sides, so we get 54 on the right divided by 6, and we get 9 on the right. Learn both sides, so we get 5x take 6 equals learn 9. And then 5x equals learn 9 add 6. So x equals learn 9 add 6 all over 5. Which is 1.6394. And we're in agreement. Okay, wonderful. So that's all handled well. Next comes the following. Some minor. Okay, now graphing logarithms. So there's only 12 problems, but I have to really understand what's going on. Identify the domain and range of each, then sketch the graph. All right, so you can only take a logarithm of a positive number as far as we're concerned. So x take 1 has to be greater than 0. That's simply the domain. So in other words, if x take 1 has to be greater than 0, then x has to be greater than, well, 1. And as for the range, well, the range of the logarithm is typically like 0 excluded. Just the strictly positive numbers. All right, but this time I'm taking away 5, so I believe that the range, you could sort of encapsulate that by like saying it's this open interval here like that. But we'll see. We'll check the first one and see what happens. Okay, and then we need to sketch the graph. So the typical logarithm would look, I mean, let's do log base 6 of whatever first. That's log base 6 of whatever. And then log base 6 of x take 1. So that's going to cause it to shift to the right by exactly 1 unit and then shift downwards by exactly 5 units. So I think it looks like that. Right, but we have to check this one. The range is all reals. What are you talking about? How can that possibly be the case? I completely disagree with this. No, I completely disagree with their answer for the range being all the reals. No, it's not. And in fact, we must check. We must be thorough. We must be accurate. So, identify the domain and range of quickly ask Gemini to do this. Okay, so it's understood the question. The domain is okay, that's right. But they used interval notation. I guess I should use it for both. What do you mean? The range of the basic logarithm function is all real numbers. Am I not understanding this at all? Let me try and think carefully what they're actually saying here. Oh my goodness me. Of course. They mean I had it mispositioned in my mind. It's fine. It's fine. I'll tell you something. I did never eat shredded wheat for Northeast Southwest for years. It's just how different people process different things. Okay, so we're going to use interval notation for both. And we're going to say this goes from 1 to infinity, and this goes from negative infinity to positive infinity. There, like that. All right, second problem. Log base 5 of x take 1 all at 3. Okay. Oh no. Wait. Right, okay. That there affects the fine. So the domain, the acceptable domain is anything greater than 1, because I can only feed in positive numbers into my logarithm function. And the range will be the entire set of real numbers. Like that. So first draw log base 5 of x. Log base 5 of x will look like this. Like that. And taking away 1 actually shifts it, translates it to the right by 1. And adding 3 translates it up by 3. So for this, 1 to the right, 3 up, there. 1 to the right, 3 up, there. And 1 to the right, 3 up, there. And the asymptote is x equals 1. Beg pardon. It looks something like that. And now to check. Okay, valid. Next. I don't think sketching them is teaching me a great deal here, so I should really just point out the major points. So anyhow, the domain of this being consigned to only feed in positive numbers to the logarithm function, it must be 3 to infinity, and the range is all the reals, negative infinity to positive infinity. And here I'll just plot it directly. So we know that log base 6 passes through 1, but here the effect of the negative 3 translates it to the right by 3, and then down by 5. So green will be just log base 6 of x. The points on log base 6 of x. So that'll be this one, and this one, and that one there. And red will be the corresponding points on the transformed function. So for this one here, it's 3 to the right and 5 down. You won't see it on the screen. You won't see it there. But I'll do in the asymptote. There, like that. That's the asymptote. The domain of this one will be Mm-hmm. Oh, cool. A sort of moderately shallow one here. But it's steep there, and but all of those are translated to the right by 1 and up by 3. So this is off the screen. That's there. That's there. That's there. The asymptote is x equals 1, of course. And it sort of follows this pattern. It's vanishingly small, like very quick. There, like that. And now to check. Okay, that is indeed right. Continue. The domain is anything greater than -1. The range is the whole of the real numbers, of course. For the original one, well, it's log base 4. So it's going to pass through 1, 0, 4, 1, and 8, 1.5, won't it? And the quarter will be, not sure why I'm struggling with this one. Well, that'll be down there like that. Anyway, all right. So 1 to the left and 4 downwards. So 1 to the left and then 4 downwards. There. And then 1 to the left and 4 downwards. There. 1 to the left and 4 downwards. There. And it will have an asymptote at x equals -1. So it'll look something like that. The domain of this one will be anything that is greater than -1. The range is the reals. The reals. And for 5. Okay. All right, that's better. Okay, so 1 to the left and 1 up. 1 to the left and 1 up. 1 to the left and 1 up. Okay. Something like that. Check these two now. That's correct. And that one's correct. Okay, good. I like it. Check these two now. All good. Right, something a tiny bit more complicated, yeah? Okay. Okay. Now, you can't feed negative numbers into there. So yes, 3x at 11 has to be greater than 0, so 3x has to be greater than negative 11. And x has to be greater than negative 11 over 3. What's this? And the range... Oh, well, it's all the reals, isn't it? Wait, did I check those? I did. Okay, great. Fine. Confusion there. Right, so the regular logarithm of 4. will be in green right here. There, no, that'll be the asymptote. Now, the effect of adding on, for function transformations, I really have to develop like a more visceral, kind of immediate understanding of it, not just memorizing rules. So plus 11 in there, that's going to shift it to the left by 11. But the way that I view it is you're moving the axes to the right by 11, but the function graph itself goes to the left by 11. You can't tell the difference. Now, what does it mean to do 3x? So it means to like squash it by a factor of 3. So everything gets squashed by a factor of 3. Okay, so that means that that will get smaller. I really want to actually understand that. Now I have modern tools, so I'm going to put them to use. Y equals log. Okay, so there's the effect of tripling. Okay. Okay, so my points of interest are where it intercepts the axes. That's what I really care about. So, log base 4 of 11 is going to be 1 point something quite high up, and then take away 5. So let's say about 1.5-ish, and then take away 5, and that's negative 3.5-ish. Right, that's in agreement. And then I could do like this. Oh, look, there you go, logarithm, right? But that's lazy. What I want to also get is I want to get the asymptote. And, well, there it is, the domain, negative 11/3, which is negative 3 2/3. So, like there. And then I want the lattice points, don't I? So what I do is I put in 1, so I get log base 14. There just aren't any. That's absolutely fine. Okay, no, I realize now. So what I really want is I don't want to like do something foolish like that. So just plug in 8. Okay, so 24 add 11 is 35. Log base 4 of 35 is like, come on. Log base 4 of 35 is 2.5-ish. 2.5-ish. 2.5-ish, take away 5 is negative 2.5-ish. So there. Right? So if I do that, and I do that, like, it's okay. Yeah. Yeah, it's okay. It's all right. Just learning how to graph properly. Okay, so the domain of this. Acceptable values. 2x at 2 is greater than 0. 2x is greater than negative 2. 2x is greater than negative 1. And so the asymptote is negative 1. There, like that. And the range, please. What's the range? All the reals. So, now to not say anything absurd. 2 times 8, 16, plus 2, 18. Log base 5 of 18 is about 1.6-ish. What am I doing? I've got a calculator right here. Log base 5 of 18. 1.8. 1.8, add 5. 6.8. So there-ish. There-ish. That's point up there, which I care about. Now, next. Plug in 0. Log base 5 of 2 at 5. It's 5.43. Is that right? That's incredibly steep. Yes, it's right. That's what it basically looks like. Now, personally, I want to know when it crosses here. The y equals 6 line. So then, in other words, 6 equals that. So 1 equals that. So like 1.5. Yeah. And it'll be real steep. Okay, next. Domain. X is greater than negative 14 over 3, is it not? Range. The reals. And the asymptote is negative 14 over 3, which is negative 4 2/3. Okay, now to do the absurd point, the crazy points. .03. So like there-ish. Mm-hmm. 2.47. So like there-ish. Mm-hmm. So 2. 1.4. Why is that there? That shouldn't be there. That should be there. That should be there. It should be real steep then. Yeah, that's good. Okay, last one now. Last one now. Domain. Okay, so only positive numbers can be put into the logarithm. So 4x take 11 is greater than 0, so 4x is greater than 11, so x is greater than 11 over 4, which is 2.75. And the range will be the reals. But how to get this better? Okay, so the asymptote, the vertical asymptote will be x equals 2.75. Varish. Input 8 to get the extreme value. 32 take 11 is 21, log base 21. And then take away 2, so 2.39. So there-ish, turn off the ruler. 2.39, there-ish. Input 4, so 16 take 11, that's 5, log base 2 of 5. Take 2 is 0.32. There-ish. Oh, and I want to know the y-axis intercept, don't I? No, the x-axis intercept, don't I? So set that equal to 0, put 2 on the other side, 2 to the power of both sides, so 4 equals 4x, take 11, so 15 equals 4x, so x equals 15 over 4, which is 3.75. There you go, there-ish. Yeah. All right. Wow, what a session. Started off really fast, and then yeah, graphs are tricky business. Anyway, I'll return later. Be well.